So, last section we're going to look at this week is 7.4. And this section is on what we call trig identities. We're going to work with trig identities in 7.4, 7.5, and then in 7.6. So we'll spend the next 2 or 3 lessons on this. But remember, just kind of in general, what is an identity? Not even a trig identity, but any kind of identity. It's just an equation that is true, no matter what value you plug in for the variable. Okay, and you might think, well, how could you have an equation where you could plug in anything and it always works? Don't equations usually have like one answer to them or 2 answers to them, like a quadratic? Well, think of this equation. And I asked you to solve that. If you distribute out what's on the left, what do you get? Chris?
3x plus 6.
You get 3x plus 6. And if you combine like terms on the right, what do you get?
3x plus 6.
You get 3x plus 6. So if you subtract 3x from both sides, you're left with 6 equals 6. That's an identity. That's a true statement because 6 equals 6. Which means no matter what value you plug in for x, this equation will always be true because it's the same thing on the left and on the right. On one side, you might consider it a little bit more complicated because you haven't combined like terms. But on the other side, you've written it factored. Right? So that might be considered simplified. And that's basically what we're going to be looking at. We're going to have something on one side, something on the other side. And they're going to be, or the question is going to be, are they the same thing? With an algebraic equation, you just do the distributive property, combine like terms, and then you can figure out if they're the same. When you put trig in the equation, it can get a little bit harder, but that's what we're going to try to go through. So, an example of a problem, and we're not going to do this yet, but here's a trig problem. And I'm going to want you to take this and simplify it as much as you can. Is there a shorter way of writing this that means the same thing? That's going to be the goal. So I don't think we're going to be too familiar with these identities. We've talked about reciprocal. You guys know those. That's how we type something in on the calculator if we don't have a button for it. Like 1 divided by tangent is cotangent. 1 divided by cosecant is the sine. Right? So those are the reciprocal ones. But these other ones, I don't think you're going to be familiar with. So we'll write down what they are and kind of put them all in one spot so you have something you can look back to in your notes. All right, so these are the reciprocal identities. And it looks like there's 6 of them, but there's really only 3. These 2, they're the same thing. It's just rearranged. These 2 are also the same thing. And those 2 are the same thing. And if you're like, well, what do you mean by the same thing? Well, think of a different formula. Distance equals rate times time. Well, is that true? Based on the first formula I wrote, distance divided by rate equals time? Okay, Chris? Yeah, these are the same formula. All you've done is rearranged it. Well, these are exactly the same thing too. All you've done is rearrange them. So if you flip the sine, you get the cosecant. If you flip the cosecant, you get the sine. If you flip cosine, you get secant. If you flip secant, you get cosine. It just changes it back. Okay, so these are called reciprocal identities. Again, there's really 3 of them. The next group of identities are called the quotient identities, or you can also call them cotangent identities. And it says that tangent is equal to sine over cosine. Cotangent is equal to cosine over sine. And that should kind of make sense if you think about tangent and cotangent, because tangent and cotangent, you flip one to get the other. So if tangent is sine over cosine, then when you flip that numerator and denominator, it should be the cotangent. And it is. Now, let's say we had something like this. Tangent squared. What does that mean? If you didn't write that with an exponent of 2, how would you write that out? Jake?
Tangent x times tangent x.
Yeah, it needs to multiply. It's just like if you're at x squared, it needs to do x times x. Well, this means tangent times tangent. Now, think about what we just said. Tangent is sine over cosine. So this is sine over cosine. This is sine over cosine. And if you multiply those together straight across, what do you think sine times sine is? Yes, yep.
Sine x squared.
Yep, so sine squared x. And what do you think cosine times cosine is? Yeah.
Cosine squared x.
Cosine squared x. So my point is this equals this. That's not another identity. That's really just using the one I showed you before, and you had a higher power. So what do you think this would be? Without going through all that and writing it as tangent, tangent, tangent. Tangent cubed would be, yeah?
Sine cubed x over cosine cubed x.
Yep. We generally don't have to deal with powers that are higher than 2, but I'm showing you that you could technically use this rule or this identity for any power. So you could say in general, tangent to the n equals sine to the n over cosine to the n. Most of the time we use it with the first power. Most of the time. Same thing here. Cotangent to the n equals cosine to the n over sine to the n. In fact, all these identities that I've given you so far, you can use them with higher powers. If flipping the cosecant gives you the sine, then flipping the cosecant squared would give you the sine squared. So if you want to fill in an n, you can. I'm not going to do it on every one of them. But these identities work with higher powers. If you flip sine to the n, you get cosecant to the n. So those are reciprocal and quotient. In the last group, those are called the Pythagorean. These identities are the way they are. You can't use them with higher exponents. Pythagorean identities specifically work with exponents of 2. And think about the Pythagorean theorem. It's all things that are squared. That's where they get their name from. So the first Pythagorean identity is sine squared plus cosine squared equals 1. The second one is 1 plus tangent squared equals secant squared. And the third one is 1 plus cotangent squared equals cosecant squared. Now, all those identities that I just gave you, the reciprocal, tangent and cotangent, and Pythagorean, I have all those memorized. So, okay, there's about 3 plus 2 plus 3. So it's about 8 of them to remember. In general, there's hundreds of these identities, maybe even thousands. But there's some that are used often, and these are the ones that are used a lot. Most of the time, if you have to use an identity that's not one of these, like if you're in a calculus class or you're doing something with engineering, a lot of times you just look up the identity. There's charts of these things online, it's pages and pages of these things. You just reference whatever one you need, you look it up and you use it. Identities aren't really something that you try to memorize every single one of them, because there's just too many. Memorize the basic ones, and that's about it. Now, what you can do with something like this, you could subtract cosine squared from both sides. That's not a new identity, that's just moving something to the other side. If you did that, you would have this. Minus the sine squared to the other side, you have cosine, oh, I did it the other way. Well, I minus the cosine squared to the other side. I'll do the sine squared now. That's two different ways of rewriting the same identity, just by subtracting something and putting it on the other side. Same idea as this. Those are not two different formulas. It's just the same formula, but you move something to the other side. Okay, and you can rearrange any of these. I could put the tangent squared over on the other side, right? I can rearrange it any way I want. And what we're going to do with these formulas is basically, it's like substitution. You're going to be given a problem, and you try to plug in something to your problem that makes it simpler than what you started with. So in the real point, like where you would use these, it would be used in fields that utilize calculus. That's where these are used. If you're not really doing something with calculus, not really going to use identities in math. Even if you do something else in math, these are very specific to calculus and trigonometry. And the whole goal is to take an expression that you're given and simplify it. Because if I have to do calculus with this is kind of a pain. It's two different trig functions, and it has a fraction. If I can simplify this, so there's no fraction anymore, it would make anything else I have to do with it easier. And that's the goal. Can we somehow get rid of that fraction? And we'll see when we do it if we can. So there's three basic tricks I'm going to show you to simplify identities. The first trick is to take everything in your problem and change it all to sines and cosines. Every single trig function can be rewritten with just sines and cosines. So technically you don't need tangent, cotangent, secant, or cosecant. You can do everything in trig with just sine and cosine. That's also like saying you could wash your car with a toothbrush. I mean, you could, but it gets a little annoying if that's the only tool you have. It'd be nice if we had other tools, and that's where the tangent and the other ones come in. Make some things a little less annoying to do. All right, so let's try this first one, and I'll show you how these kind of work. Okay, so the first problem says simplify, and we have cotangent divided by cosecant. Let's try the first trick that I just explained, which is change everything to sines and cosines. Okay. Can someone tell me how you can take cotangent and rewrite it so it's using sines and cosines? Eli?
Cosine over sine.
Yep, it's cosine over sine. How about the denominator? How can we rewrite cosecant using sines and cosines? Could be both, it could just be one of them. Yep.
I could just write it as sine of theta.
This is equal to sine theta?
No, 1 over sine.
1 over sine theta, yep. And that's the other thing about identities, unfortunately, you make one little mistake like that, and then the whole thing is messed up. So they're very easy to mess up. Okay, so that's what we have now. What we have there is a fraction divided by a fraction. You would handle that exactly the same way you would handle it if it was numbers. If you want to divide two fractions, how do you do it? Jack, do you remember how we divide two fractions?
No, it's been a while.
Anyone remember? How do you divide two fractions? Zach?
Isn't it multiplied by the reciprocal?
Multiply what by the reciprocal?
The denominator.
No, not the denominator, but we're on the right track with multiplying by the reciprocal. Let's stick with that. Yep.
Don't you flip it and then do like the butterfly method thing? So like the top and the bottom multiply and then top and bottom multiply. Like the opposite.
Maybe. I'm not sure. We'll see when we write it. Maybe that's what you're thinking. It's not cross multiplying if that's what you're thinking. Like when you solve a proportion, you multiply the diagonals. So yeah, we're not doing that. But anyone kind of finish that off for me? We're going to multiply by the reciprocal, but what are we multiplying by the reciprocal? And what are we taking the reciprocal of? The top or the bottom? Yeah?
Isn't it both? Like of the entire equation?
Nope, just one of them. Yep.
You're multiplying the numerator by the reciprocal of the denominator.
Yes, you're multiplying the numerator, that stays the same, by the reciprocal of the denominator. You're going to do it exactly the same way. Everything that we really do with arithmetic, we can do the same thing with trig. So keep the top the same. And then multiply the bottom, or multiply by the reciprocal of the bottom. Now, what's going to happen when I multiply those two fractions together? It'll be the same thing that would kind of happen here. Yep.
Well, the signs cancel out.
Yeah, the signs would cancel out. Whenever you multiply two fractions, if you have the same thing in the top and in the bottom, it cancels out. Now, if you're adding two fractions, and it has the same thing in the top and the bottom, no, it doesn't cancel. The only thing you can do when you're adding fractions is common denominators. But when you're multiplying fractions, you can cancel if you have the same thing in the top and the bottom. And now, what am I left with? Chris?
Cosine theta.
Yeah, all I'm left with is cosine theta. So I took an expression that had two trig functions with division, and I turned it into a single trig function, no division. And this means exactly the same thing as what I started with, but it's a much simpler way of saying it. And that's what a trig identity is. That's the goal of what we're trying to do today. Any questions on that? Okay, let's try another one. This one's about the same difficulty as the last one. And the trick here is going to be to change everything to sines and cosines. So let's start with cosecant. Abigail, how can I rewrite cosecant? Good, just like you type it in on the calculator, 1 over sine. And Casey, how can I rewrite tangent? What is it? True, but if we do it that way, it won't help us here. How do we want to rewrite tangent in a way that will help us here? Yeah, we want to write it as sine over cosine. I'm not saying you won't ever do it the way you said, but at least for these first few, we're going to try to write it in terms of sines and cosines. That turns into sine over cosine. And Francesca, what's going to happen there?
We're gonna multiply it now?
Yeah, we're going to multiply, and what happens even before I multiply?
Oh, we would cross out the sine.
Right, because you have multiplication, and you have the same thing in the top and in the bottom. Remember, you can't do that. It's addition. We'll talk about that. But it's multiplication, so we're okay. And if I cross those out, Ethan, what does that leave me with?
1 over cosine.
1 over cosine. And Chris, what do you get if you take the cosine and you flip it? Or, I'm sorry, yeah, if you flip it, what is that?
Secant.
That's the secant. So again, we took a problem that started with 2 trig functions, and we turned it into something that only had 1. Any question on that? All right. Now, these last 2 problems, they're what I call, they're more of like an open-ended problem. With a simplify, you never know when you're done. You just kind of keep going till you think you get something that you can't go any further with. Like when you're down to a single trig function by itself, you're not really going to be able to do anything else with it at that point. There's another kind of problem. We'll do this one in a little bit, not yet, but it's called verify. With verify, they give you something to start with, and they tell you what it's going to simplify to. So with a verify problem, you know you're done when you take this side and you turn it into this side. So it's like knowing the answer ahead of time that you're going to get. So that's why I think verify is a little easier. Okay, so when you're asked to verify a trig identity, your job is to show that the equation is true. How do you do that? You turn one side into the other side by simplifying it. So when you do a verify problem, what you want to do is pick a side to start with and leave the other side alone for the whole problem. Don't touch it. Well, how do you know which side you should try to work with first? Technically, you could pick either side, but the best way to do it is to pick the side that you think is more complicated. It's always easier to take something that's complicated and try to simplify it. You never want to start with something simple and try to complicate it to look like something else. So always start with the side that looks more complicated. Generally, that should be pretty obvious, which side looks more complicated. If you can't figure out which side looks more complicated, then you can probably start with either side, and it won't make a difference. So one trick we learned was try changing everything to sines and cosines. Another trick is to write with a common denominator. Let's just review that really quick. Let's say I wanted to add these two fractions up. Does anyone remember how you find a common denominator? Yep.
On the common denominator, you would just like multiply the denominators.
Yeah, doesn't matter, you just multiply the two denominators that you have together, and that's the common one. So now, you have to go back and say, well, how do I turn each denominator into 15? What would you multiply the top and the bottom by on the left to make that 3 into a 15? Yeah. This fraction gets multiplied by the other denominator. Same idea here. This fraction gets multiplied by the other denominator. And it's not going to matter if it's a 3 and a 5 or a sine and a tangent. You do exactly the same thing. Multiply each fraction by the other denominator. Now, there's one time we wouldn't have to change both. Let's say you had something like this. What's the common denominator in that problem that I just wrote? Yeah?
3.
It's 3. When one of your fractions is already the common denominator, you don't have to change it. This fraction wouldn't have to change the 2/3. All you'd have to do is multiply one of the fractions by the other denominator, not both of the fractions by the other denominator. Okay, but that's only if one of your denominators is a 1. Okay? All right, so let's look at this. And when you first look at this one, you might not even be thinking common denominators because there's no fractions. Right? Not every trick is going to come up in every problem. But let's just kind of work through it and see if fractions come up in this problem. And if they do, maybe the common denominator would help. Okay, there's a property you can use here that we use all the time when you have something on the outside of parentheses and you have addition on the inside. Anyone know the name of the property I'm thinking of? Yeah? Distributive property. That property works just like it would here as with anything else. If you were thinking, well, maybe I could change everything to sines and cosines, you're also right if you do that. You have to do both. You're going to have to distribute, and you're going to have to change to sines and cosines. Let's distribute first. So we have sine times cotangent plus sine times tangent. Okay, so I distributed out the sine. Now, let's change everything to sines and cosines. If it already is a sine or a cosine, you can put a 1 under it. But other than that, there's nothing else you have to do with something that's already a sine or a cosine. So let's look at cotangent. How can we rewrite cotangent? Yep, Haley. All right, so I have cosine over sine. Now, since that's a fraction, if I make one thing a fraction, I'm going to make everything a fraction. So let's make this sine over 1 plus, I'm going to do the same thing here. Let's make this sine over 1. And what is tangent? Yep, sorry. Sine over cosine. Okay, now remember what I said. Think of a plus or a minus sign in a problem as like a wall. You cannot cancel across a plus or a minus sign. Only a multiplication sign. So if you're thinking, oh, maybe I could cancel this sign with this sign, no, you can't. You can't do that. Okay, that plus sign stops you. But is there anything here that appears in the top and the bottom through a multiplication sign? Okay.
On the left side, the two signs.
Yep. These do cancel. That's perfectly fine. It's like you have two little problems here. The problem to the left of the plus sign and the problem to the right. Plus sign breaks it up. So now on the left, we have a cosine. And in the bottom, we have a 1. Plus, let's multiply those two fractions together on the right. What do you get in the top if you multiply those together? Yeah.
Sine squared.
Yep, you get sine squared over, what do you get in the bottom? Yep, cosine. Okay, so you've changed everything to sines and cosines. You've used that trick. That trick is done. What's another trick that we just learned that now, I think, pops up in this problem? Yeah?
Cancel the cosine, so.
Can you cancel across a plus sign? What do you think? Can you cancel across a plus sign? No. Remember, that plus sign stops you. It's two separate things. You can't cancel. If you think you can, try it with numbers. Pick numbers. 3 over 1 plus 2 over, actually no, it would be a 3. Right, so I just changed the cosines to 3's. If you say you can cancel the 3's out, then that means this would be add up to 2. Because you'd have, the 3's would be gone and you just have 2 over 1. But there's no way if I take 3 and add 2/3, I'm going to get 2. So that just doesn't work. Anyone have another idea about what we could try next? Yep?
Find a common denominator.
Find a common denominator. So that's what we'll try. You find the common denominator exactly the same way you would do it if it was numbers. No different. Anyone think they can tell me my common denominator? Chris?
Cosine theta.
Cosine theta. It's the product of the two denominators that you already have. And I told you that when you have a fraction that already has a 1 for one of your denominators, you don't have to change both of them. So the fraction on the right, we can leave that alone. What would you multiply the fraction on the left by to make it have the common denominator of cosine? Sarah? Cosine. You multiply this fraction by the other denominator. It's exactly the same thing I said with numbers. This fraction by the other denominator. Cosine over cosine. Good. Now you've got a common denominator of cosine in the bottom. And you have cosine times cosine. We're going to put that right here. What's cosine times cosine? Jake?
Cosine squared.
Cosine squared. And now we've used up all the tricks that I taught you. We've changed to sines and cosines. You rewrote it all with a common denominator. Now there's something there you have to recognize. Something that's written there turns into something else that we wrote down earlier. Probably not the bottom, because think about the bottom. The bottom is just a trig function all by itself. What are you going to do with that? But the top has a lot more going on. So that's what I would focus on and see if you can turn it into something. Cosine squared plus sine squared. What is that? Ashley?
It would equal 1.
Yeah. Anytime you end up with a sine squared plus cosine squared, or cosine squared plus sine squared, it's like saying 2 plus 5, 5 plus 2, same thing. Anytime you end up with that, you can turn that all into a 1. So this turns into this. Now we're starting to get something that's pretty simplified. What's 1 over cosine? Yeah?
Secant.
Yeah, secant. And at that point, you're done. There's nothing else you can do with that. It's a single trig function. There's no arithmetic, there's no fraction, just secant. It's as simple as you can get it. So look at what you started with. 3 different trig functions with a distributive property, and it all simplified to just secant. Okay? Just following those 2 tricks. Change to sines and cosines, and rewrite with a common denominator. Those are the only 2 tricks we had to use in that problem. In the identities, you don't have to memorize them. Even if we were having a test in person, you wouldn't have to memorize them. I would suggest you put them all on your reference sheet. Okay, but that's what you want to do. Just look up the identity anytime you want to use it. Don't even try to memorize it right now if you can. Just look it up. Any questions on that one? And that one would be more of like a medium. First 2 problems, I would say those are easier. This is a little harder. Got some more steps in it. Let's look at this one. So this is our first verify. Okay, again, I like verify better because I know when I'm done. Look at the side that's more complicated, which in this case, can someone tell me which side looks more complicated? Eli?
The right.
Yeah, definitely the right side. So in this whole problem, we're going to work with the right-hand side. And we're going to keep using all the tricks that we've learned so far. And hopefully when we're done, the right-hand side looks exactly like the left-hand side. That's the goal. Okay, but at least we know when we're done this time. When we get sine, we're done. If we never get sine, we're not doing it right. All right, so I'll ask you guys this time. Anybody have a thought what I try first here? Yep.
Convert tangent and cotangent to sine and cosine.
Yeah, I would even convert everything. I would convert the
Oh,
entire right-hand side all into sines and cosines. So if we start with the top, that's 1 over cosine. And the bottom, well, tangent is sine over cosine. And cotangent is cosine over sine. Now, the bottom part of this fraction has a lot more going on with it than the top. So I wouldn't worry about the top right now. That 1 over cosine is probably just going to hang out there for a while. But I would work with this like it was its own separate problem and just see what you can do with the bottom for now. Right? I'll keep copying the top over, but I'm not going to do anything with it until I see what I can do with the bottom. Okay. Any thoughts what I can do with those 2 fractions in the bottom? And you have very limited options. I've only told you 2 things you can do, and one of them you've already done. So it's like I'm telling you to turn left or right, and I'm saying don't turn left. Only have one thing left to possibly try. Yep,
Common denominator.
find a common denominator. Even if you have no idea how that's gonna help you, just try it and see if it works. What's the common denominator between those two fractions? Yep,
Cosine theta times the sine theta.
yep, it's the cosine times the sine. Now, what do we have to multiply? Because each of these, we have to fix it so it has the common denominator. What does the fraction on the left get multiplied by? Top and bottom. Yep,
By sine of theta.
by sine of theta. So I don't have a ton of room on my space here, but I'm just going to squeeze it in. Sine times sine. And what does the fraction on the right get multiplied by? So think about what you have to multiply the bottom by, and then you have to do the top by the same thing. Yeah?
Cosine of theta.
Cosine of theta. Cosine theta. Cosine theta. Now, let's write down what we have. Now, what am I going to have right here? Give you a hint. There's nothing in your notes at this point that's going to help you. It's something you have to simplify that's only on the board. Well, can you explain to me what's happening right here? What's going on right here? What are we doing?
We're multiplying sine,
Where?
top and bottom.
Exactly. We already did it in the bottom. Right? When we do it in the bottom, we just have the cosine times the sine.
Oh, yes.
So now just do it in the top.
Sine squared.
Sine squared. So we have to finish that part off. We have sine squared. And what's going to go, Abigail, what's going to go right there?
Cosine squared.
Cosine squared. We already did the bottom. Cosine times sine. Let's do the top. Cosine times cosine. Cosine squared. All right. So we've got that part. Again, copy the top over. Not doing anything with that. But look at the bottom. Does anybody see something that simplifies in the bottom? And it's something we've done. Yep.
The sine squared of theta plus
Cosine.
cosine.
Yep. What happens to sine squared plus cosine squared?
It equals 1.
That all equals 1. So look at all that stuff we just got rid of. Now we just have 1 cosine times sine. Now, you have a fraction divided by a fraction. You've already done that. Someone remind me, what did we do before when we had a fraction divided by another fraction? Yep,
Multiply the numerator by the reciprocal of the denominator.
exactly. Keep the numerator the same and multiply by the reciprocal of the denominator. That's your denominator. That's your numerator. So it's going to be sine cosine over 1. Okay. And what happens there, and that'll pretty much give us our final answer. Okay. Yes, you have all multiplication, no plus sign, right? So you can cancel out the cosines. You can also cancel out the ones. And what's the only thing that we're left with?
Sine of theta.
Sine theta. Yep. So we found a much simpler way to write down this whole thing. We got sine theta. But look at what it said we were supposed to get. Sine theta. We we got sine theta. They told us it should be sine theta. So we know we got it right and we're done. Right, so that's always the last thing you do in a verify. Scroll back up and see if what you got matches what they said you should get. And I would consider that one again, that's more of a like a medium one. That's not as easy as the first two. I would say on the test you'll have one kind of medium one, like that. And you'll have maybe 5 or so of problems that are more like that or like that. Any questions on that? All right. So for tonight, okay, we're not going to do that. We got take home test, and that's on 7. What did we start with this week? 7.2, I think. 7.2 through 7.4. Okay, this would be due by 9 a.m. Eastern time, not Western time or anything like that. 9 a.m. Eastern time on February 4th of this year.
We can't turn it in last year?
No, not last year, not next year. Okay, it would be on Edge Elastic. You would have 90 minutes. So you have 90 minutes to complete it, and it will be open between, actually, you know what I'll probably do? I'll just set it to 100 minutes. Let's make it a nice number. 100 minutes. So you have 100 minutes to complete it. And it doesn't have to be continuous, so like if you start it and you pause it and you want to go back to it, that's fine. But make sure if you do pause it, just close it, because the timer will keep running. Like if you just walk away and just leave it open, it'll think you're just staring at the screen. So close it up. Okay, if it's not in by that time, it would just be like not turning in, a testing class. If you just sat there and didn't take it, it would be a 0. Does anybody have any questions about that? Anybody here that doesn't think that they can get that done or would prefer to do it a different way because you're not available tonight for whatever reason? Okay, so I will open the test up before the end of school today. I have to do that, so probably by like 2:30, the test will be open, and you'll have until 9 a.m. tomorrow morning.